Okay, chemical reactions. One of the main things that we as chemists deal with are chemical reactions and being able to write chemical equations. Today we're going to talk about 5 types of chemical reactions. And when we start dealing with chemical reactions, there's things we have to understand. First of all, anytime we have a yields arrow, the yields arrow will take us from the reactants, which are always to the left of it, and then the products, which are always to the right. Right? And then this is law of conservation of mass. Your reactants are going to have the same mass as your products. You're not going to lose or gain mass in this chemical reaction. Sometimes it may appear so, but a lot of times that may be because a gas is forming. Okay? And if a gas forms, you're not losing it. You may not capture that gas, but that's still, you'd have to capture the gas. And then if you compared the total mass of the reactants, they would equal the total mass of the products. So then you're dealing with your law of conservation of mass there. Okay? Matter can neither be created nor destroyed, right? So we can't really create or destroy it. We're just rearranging it is what we're doing here. Also, when we run these chemical reactions, you're going to see a subscript. If we have a little S subscript in parentheses, that means that the substance is solid. If we have a script L, that means that it's liquid. If we have a G, that means it's a gas. And if we have an AQ, that means it's aqueous. Okay? And aqueous means it's dissolved in water. So it's a solution. Okay? And that's typically the phases that we will see these in. Right here. Okay? 5 types of reactions. First type we will go over. Is a synthesis reaction. Okay? It's what the Beatles were singing about when they sang the song Come Together. Yeah, it's all about synthesis reactions. So anytime you listen to that song, you know what they're dealing with right here. Oh, this is about synthesis reactions because, John Lennon, this was his favorite of the 5 types of reactions. With the synthesis reaction, we are bringing things together. Okay? So, for example, let's say we have hydrogen gas plus O2 gas yields water. And in this case, there's going to be enough heat given off. That's going to be water in the form of gas. We're not going to worry about balancing it. We are going to worry about getting the formulas correct first. That's why in the last unit we did chemical formulas. Our formulas must be correct. Okay? You will notice that hydrogen and oxygen are what we call diatomic. It's H2 and it's O2. Diatomic, 2 atoms. There are 7 diatomic elements. And when we look at the periodic table up there, I've outlined the 7 in blue. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. There are 7 that form a magic 7 on the periodic table. You can see that they form a 7 here. There's 6 of them there, but then we've got the hydrogen right there. Whenever they're by themselves, they form diatomics. We have to make that. Don't just put oxygen as O. It's always O2. Unless it says ozone, then it's O3. But if it's oxygen, it's O2. If it's nitrogen, it's N2. If we have chlorine gas, it's Cl2. They're diatomics. Okay? Just recognize those. Keep those in mind when we're writing chemical formulas. So those are the diatomics. I'm not balancing this, but you can see that they've come together to form one thing, one compound. So we have two or more elements coming together to form a compound. That's a synthesis reaction. The exact opposite of the synthesis reaction is a decomposition. This is the tearing apart reaction. Okay? So, if we have a decomposition reaction, for example, let's say that we have, oh, here's a good one. HGO, mercury 2 oxide, was a red powder. If you were to heat this, it would decompose or split into liquid mercury and oxygen gas. And again, I'm not worried about balancing them today. Worried about just getting the formulas correct. That would be an example of a decomposition reaction. Okay? Another decomposition that we see is hydrogen peroxide. And a lot of times we'll just call this one, well, it's actually, we'll just say that it's a liquid. Okay? It's usually they're dissolved in water. It's usually aqueous because we have hydrogen peroxide. It's 3% hydrogen peroxide solution, but we'll just say we have liquid hydrogen peroxide here. Okay? If you have a cut on your skin and you put hydrogen peroxide on it, it decomposes into water, which is a liquid, and oxygen gas. Okay? Basically, what we're doing is we're saying, well, sometimes when we get a cut, we get anaerobic bacteria on it. Okay? And oxygen is toxic to those anaerobic bacteria. So we put hydrogen peroxide, it bubbles. Okay? Now oxygen kills some of those anaerobic bacteria. So these are decompositions. They're kind of mirrors of one another. You know, synthesis, where two or more are coming together to form one compound. Decomposition, we always start with one compound, and then we have the arrow, and it decomposes, okay, or breaks down. A lot of times into its elements. Not always, okay, but it can decompose into its elements there. All right, so there's two of our reactions right there. We've got three more, right? The next one is called a single replacement reaction. Okay? Single replacement. With single replacement, typically you're going to start with an element and it's going to switch places. So it's kind of like you're at the dance, right? You're out, you're dancing with your partner at the dance. Oh boy, you know, this is nice. You know, great night, great music. You smell so good. Okay. And then there's somebody standing over against the wall and they're saying, "Doll, I don't like it here against the wall. I wish I were dancing." So they walk out and they tap you on the shoulder. "Do you mind if I dance with your date?" "No, not at all. Go ahead." And then you step back, steps in, and you walk over and stand against the wall. "What have I done to deserve this? It was so nice. She smelled good. The music was great. It's a great night dancing. Now I got to stand against the wall." Okay? They switch spots. That's what happens here. We have a switching of the spots. They're kind of like changing dance partners. Okay? And there's a couple ways we can do this. Let's say, for example, we have this. Let's take let's take copper, solid copper, and let's put it in silver nitrate solution. All right. When you look at this, folks, is a metal. It wants to switch places with the metal. Okay? We are not going to put the two metals together. This metal, here's a metal, and this is a non-metal. The metals want to dance with the non-metal. So they're going to switch spots to dance with the non-metal. So then we get silver, okay? And it ends up being copper 2 nitrate. This is aqueous, and this is our solid. Notice how the metals switched. An example of this would be, let's say I've got some silver nitrate here. Okay? Oh, let's see. Need a little one. And I've got this little beaker. I'm going to put some silver nitrate in this little beaker. Okay? Right here. Looks clear. It's aqueous. Okay? Then what I'm going to do is I'm going to take some copper wire. Oh, I left my scissors in there. I'm going to cut this piece of copper wire. So now I'm going to immerse this copper in this silver nitrate. And we will get that switching. You're actually noticing the silver nitrate's decomposing. It's actually turning black right now because the light will cause it to decompose over time. But what I'm going to do is I'm going to leave this in there. And in a little bit, we're going to pull this out. It's going to have some silver actually on it, okay, as this single replacement reaction occurs. Okay, now, let's say we have this. Let's say we have a nonmetal out here, like chlorine, Cl2, which is a gas, and we bubble that through a solution of sodium bromide, which is aqueous. Now, this one is a nonmetal, okay? The nonmetals are going to fight for the metal. You have to identify the one that's by itself, what it is, okay? Then they switch. So the chlorine is going to switch with the bromine this time. because the nonmetals are going to switch. And we are going to get bromine, Br2, which is a diatomic. And also, if you look at the periodic table, it's blue, so it's a liquid at room temperature. And we're going to get sodium chloride solution, aqueous. So now our nonmetals switch. Notice, when we make these compounds, I never put two metals together up here, and we don't put the two nonmetals together here. Okay? So make sure we're doing that. If you're putting two metals together, you're doing it wrong. If you're putting the two nonmetals together, you're doing it wrong in this one. Yes?
Would we treat the metalloids like nonmetals?
Yes, treat the metalloids like nonmetals.
Okay.
Yep, good question. Any other questions? Okay, so that's single replacement right there. Next, double replacement. Notice how I'm just getting the formulas correct, folks. The last one was sodium chloride. Na was a 1 plus, Cl was a 1 minus. So I hook them up together. Okay? The formulas, getting the formulas are correct. Then tomorrow we'll worry about balancing them. But today, get your formulas correct. Double replacement. Now, this is if you have two people out dancing, or four people. Guy and a girl in one group, guy and a girl in another group. And they're going, oh, next song, let's switch partners. Hey, that sounds great. So when the music starts, the one steps away, goes over to the other partner, and they switch. And that's what's happening here. Let's say, for example, we brought back this, silver nitrate solution, and we've got some potassium iodide solution. Okay? So silver nitrate, AgNO3, which is aqueous, and we have potassium iodide, Ki, which is aqueous. These are correct because silver is a 1 plus, nitrate's a 1 minus. Potassium's a 1 plus, iodide's a 1 minus. So we're good. We're going to take some of this silver nitrate, and we're going to squirt it in this test tube. Then we're going to take some of this potassium iodide. And we're going to squirt it in this test tube. And you can see we got a cloudy yellow. That is a reaction. That cloudy yellow, or the cloudiness, is what we call a precipitate. Okay? It is the solid that came out. And it shows us that we have a reaction. Okay? So, when we go back and look at this, anytime we're doing this, we switch the metals off the front. We're going to take the silver and switch it with the potassium. Again, do not put the two metals together here. Metals and nonmetals go together. So we switch them. So the potassium's leaving the iodine and going to hook up with the nitrate. KNO3, which is aqueous. Remember, the K is a 1 plus, NO3 is a 1 minus, so they hook up 1 to 1. So our formula is correct. Then we look at the silver. The silver, Ag is a 1 plus, iodide is a 1 minus. They hook up 1-to-1. And these are on your ion sheet, folks. So we get AgI, which ends up being a solid. That is the yellow solid that we see here. That is the silver iodide. And anytime we get it to be cloudy in these are another name for our precipitation reactions, we know that a reaction did occur. If it stays clear, no reaction occurred. But here we go. We got a reaction in that one, folks. Okay? Questions so far? Double replacement. Yes.
At the very beginning, you said that you couldn't like destroy mass, but couldn't you turn it into like heat or light or something?
The heat is usually given off from the electrons. Usually the electrons are going to a lower energy state because of that. And so as they do so, they're transferring their heat or giving it off, releasing it into the environment. A lot of these are going to be either exothermic, releasing heat, or endothermic, acquiring heat because of the breaking and the formation of the bonds. So the heat's not coming from mass, it's coming from the changing of the potential energy of the substances. Okay, that's a fair question. That mass is actually going to be done is going to happen in nuclear reactions, and that's where you go back to Einstein's equation. The mass is going to be converted into small quantities of energy. So it's two different phases of really the same thing. Okay. But that's double replacement. The last reaction is combustion, folks. Okay? And the combustion reaction is usually going to be a hydrocarbon, which is carbon and hydrogen in some proportion. Call this a hydrocarbon, because that's hydrogen and carbon, okay, in some proportion. Then it's always going to react with atmospheric oxygen to give us carbon dioxide and water. Okay? This part of it is always going to be the same. We'll have to balance it, and we'll talk more about balancing that thing tomorrow, but that's always going to be the same. Okay? So for example, if we were to light the methane coming out of these gas jets in here, methane is a hydrocarbon, CH4. It is a gas. Okay? It reacts with oxygen, atmospheric oxygen, to form carbon dioxide gas and water vapor. Notice how this is the same. I may change this. Let's say we're burning gasoline, which contains a lot of octane. Okay, octane, let's say is C8H18. And then it reacts with oxygen to form carbon dioxide and water. Notice how this is the same throughout. These are relatively easy. Hey, you've got carbon and hydrogen in some proportion. We're going to react with oxygen in our atmosphere, and we're going to get carbon dioxide and water vapor. Okay? So these are our 5 types of reactions, folks. Synthesis, decomposition, single replacement, double replacement, and combustion. And by the way, here's our silver forming on our wire. that silver metal now coating it. It took us a little bit of time, but if we left it in there, it'll actually be kind of furrier. These are silver crystals actually forming on the copper wire. And that's our single replacement reaction right there, folks. Okay? So now what we've got is I've shared with you a flex book. And if you go to skill practice 28, you're going to see that there's the different types of reactions there. Make sure you're getting the formulas correct. That is the big thing. Identify the type of reaction that we're dealing with and make sure your formulas are correct. Okay? Because that'll help us when we start balancing equations tomorrow. All right.